This is AS Chemistry, Chapter 5, Lesson 1 on collision theory. So let's start by looking at this term, which is rate of reaction. A rate of reaction is essentially how fast is the reaction. So how fast is the reaction going? Has it got a high rate of reaction or has it got a very low rate of reaction? The rate of a chemical reaction is measured as the amount of reactant used up or product made in a certain time. And we'll look at this in a bit more detail in a minute. The definition of the rate of reaction is that the rate of reaction is the change in concentration of a substance in a given time. So the definition of the rate of reaction is it is the change in concentration of a substance in a given time. Or alternatively, you can write this equation in the exam as the definition for the rate of reaction. So the rate of reaction is equal to the change in concentration of a substance divided by the time. And that is the same as the definition. So it's the change in concentration of a substance over the time. Now what's interesting is we've got to really understand what do we mean by the rate. We've really got to understand that. And as I've written, it's the amount of either reactant used up or product made in a reaction in a certain time. So think about it. When a reaction takes place, the reactants will collide and they will hit each other, they'll react, and they'll be used up over time. And as the reactants come together and they react with each other with some kind of chemical reaction, they'll form products. So the products are always being made in a chemical reaction and the reactants are always being used up in a reaction. You can either monitor how the reactants are used up against time, or you can either monitor how the products are made against time. And what you can do is you can plot a graph. So you can plot a graph of either the amount of product made against time, or you can plot a graph of the amount of reactant used up against time. And by looking at the shape of the graph, we can by looking at the shape of the graph, work out, if you've got a couple of lines on the graph, work out which reaction is faster. But we'll look at that later on as we go through the lessons. But once we've plotted the graph, we get a set shape. The shape for the amount of product produced against time and the amount of reactant used up against time is always the same. So the general shape of these graphs is the same, and we'll see that in a minute. And what we can do is we can determine the gradient of the graph at a set point, and that will allow us to work out the rate of reaction. And I'll talk more about that on the next slide. So the rate of the reaction is essentially how fast is the reaction. And you can work out the rate of reaction at any time you want during the reaction. But in order to do that, you first have to either monitor how the reactants are used up against time or monitor how the products are produced against time. You then plot a graph, and then at whichever time you want, you can work out the rate by determining the gradient at that particular point. I'll talk through that more in a minute. And essentially, by working at the gradient, what you're working out is the change in concentration over the time, or the change in the amount of a substance in a set time period. And that will allow you to hence work at the rate of reaction. I'll show you the graph in a minute, and then what we'll do is we'll relate it back to this equation and back to this definition, just to make sure we understand that. So here's the graph for the amount of product produced against time. And as I've said before, the shape will be exactly the same regardless what product you have. So the shape will be exactly the same. So learn the shape for the exam. On the x-axis, I've put time. And on the y-axis, it depends on what type of product you have. Are you looking at the mass of product that you're collecting? Or are you looking at the volume of the product you're collecting? If the product is a gas, then usually the y-axis label will be volume of gas collected. And that's important, but that depends really on the equation that you've got and looking at the particular product that you're trying to collect. So if it's a gas, it will usually be the volume of gas that's being collected. So what does the shape of this graph actually look like? This is what the curve looks like. So it starts off very, very steep. It then gets less steep, and then eventually it levels out. Make sure you learn this shape for the exam. Whenever you're collecting a product against time, the shape of the graph will be exactly the same as what it is on this slide. Now what's very important to note is that at the very, very start of the reaction, at the start of any reaction where you're collecting the product, it will be very, very quick. The rate of reaction will be very, very quick. It will have a very fast reaction rate. And we know that because the line is very steep. And they'll ask you questions about this in the exam. The steeper the line, the faster the rate of reaction, i.e. the rate of reaction is quite high at this point. So lots of product is being produced in a small amount of time. Now let's go back to the definition of rate of reaction. The change in concentration over the time. Well, actually, if we look at this in a small amount of time, look how much product we've made. The change in, let's change the word concentration to change in the amount of substance. Look at the amount of substance we're making in a small period of time. That's quite a lot. We're making a lot of product in a very small amount of time. And therefore, the rate of reaction will be very, very high. So at the very start of the reaction, it will have a very high rate of reaction because a lot of product is being produced in a small amount of time. The change in concentration over time is going to be very, very high at this point. So very, very fast rate of reaction. As the reaction proceeds, okay, the rate of reaction slows down. So the reaction is slowing down and the line is getting less steep. So the graph is less steep and it shows that the reaction is slowing down. And eventually, in the final stage of the reaction, at the end, the line is flat. It's a horizontal line. And what that tells us is that no more product is being produced and therefore the reaction has stopped or the reaction has finished. And it's usually because one of the reactants is in excess and the one that's not in excess has been used up at this point. But this is the curve that you will get whenever you're plotting a graph of amount of product produced against time. Whether it's the mass of a product or it's the volume of a product, i.e. a gas that's being produced in the reaction. So it's always a curve which is steep at the start, it then becomes less steep, and then it levels off, it becomes horizontal at the end. The point at which it becomes horizontal is the point at which the reaction has ended. So all you do is take a ruler against the curve and work out when it's horizontal, and you can read off the time in this particular point, and that will tell you when the reaction has finished. If you now want to work at the rate of the reaction, rather than saying it's got a very fast rate at the start, it then slows down, and then the rate of reaction at the end will be zero because no more product is being produced as the time is going on. To work at the rate at any particular point, whether it's 1 minute into the reaction, 2 minutes into the reaction, or even 10 minutes into the reaction, you need to work out the gradient. Now I'm sure if you do maths, you certainly would have done a lot of work with graphs and taking the gradient of curved lines. But if you haven't, then I'm sure you've learnt lower down the school that if you've got a straight line, you can work out the gradient very, very easily just by doing the change in y over the change in x. So dy, the difference in y, over the difference in x, dx. If it's a curve, it's slightly different because you don't have a straight line. So when it comes to a curve, you have to take something called the tangent. And again, if you're not too sure on how you're taking and in looking at taking a tangent, then you might want to read up on how you take a tangent for a certain line. But we're not going to worry about taking tangents for the time being. But if you want to work at the gradient at any point of this curve, you take a tangent. That means that you draw a line next, so you make a point, or you put a cross at the time on the line that you're interested in taking the gradient at. You draw a line which is next to the curve, and then you draw a triangle and work at a change in y over the change in x. But I'm not going to go through the tangent, but it's useful to remember that if you want to work out the rate at any particular point, you draw a tangent to the line, and then you work out the change in y over the change in x, which is the change in concentration over the time, and that will allow you to work at the rate at any particular point on this graph. Anyway, moving on and keeping to this idea of the shape of the graph. So this is the shape of the graph you'll get for the amount of product produced against time. Now, if it was the amount of reactant produced against time, all you do is you take the curve and you flip it down. Okay, so you flip it up. It's almost like putting a mirror against the time axis, and it's the same line, but it's just flipped down. So the reaction starts off very fast. The reactants have used up very, very quickly. Then they slow down, and eventually it levels off. So it's literally the same line, but it's just literally flipped the other way around. So it's the mirror image of the line that you've got there for the reactant against time. But it's very difficult to monitor the decrease in reactant against time. So we tend to plot a graph of the amount of product against time because a product can be collected easily. And again, that's a horizontal line just showing you when the reaction has finished. Okay, let's look at a common type of reaction that you'll do in the laboratory and look at how we can collect one of the products of the reaction. So what we'll start by saying is that marble chips are made from calcium carbonate, which is CaCO3. And I'm sure you've used marble chips before. Marble chips will react with acids and they'll produce a salt, water and carbon dioxide. When marble chips react with hydrochloric acid, the salt produced is calcium chloride, and they also produce water and carbon dioxide. So when calcium carbonate reacts with hydrochloric acid, calcium chloride, water and carbon dioxide are produced. Now, if this is a reaction taking place, it's going to be very difficult for us to monitor the change in the reactants. Yes, we could record the mass and we could do some simple chemistry, but it's easier for us to collect the product of this reaction. So if I want to monitor this reaction against time, it's very, very easy for me to collect one of the products of this reaction. And that's carbon dioxide. Now think about why I could collect carbon dioxide very, very easily. Well, it's a gas. So carbon dioxide is a gas. I could easily collect carbon dioxide against time, either in a gas syringe, or I could collect it over water by inverting a measuring cylinder in a trough of water. So I could collect carbon dioxide because it's a gas against time, and I would get a curve that's very, very similar to before. If I tried to do this with one of the reactants, it would be very difficult to do, but there is a way that you could certainly do it. But carbon dioxide is a gas, and if you've got a gaseous product in any reaction, it's very easy to collect against time. And like I say, the best way to collect it at A level is to put a gas syringe on, which is very, very sensitive and will give you an accurate reading each time. So collect the carbon dioxide against time and then plot a graph. So if we plot a graph of the amount of carbon dioxide produced against time, then we get a graph that looks something along the lines of this here. And what we can see is, since carbon dioxide is a product, the graph is the same shape as what we saw earlier on for the product against time. In this case, it says mass of carbon dioxide produced. But when we do an experiment with a gas syringe, that axis will be changed, and that axis will say volume of carbon dioxide produced. But we can see again the curve is exactly the same. And again, we can see the reaction is very, very fast at the start. It's got a steep line. The line gets less steep as the reaction proceeds, and eventually the line becomes horizontal. So we can see this quite clearly. Now, when we do the experiment with marble chips, the marble chips are usually in excess, and the hydrochloric acid is the reactant, which is not in excess. And as the reaction proceeds, the acid particles will get used up, and then once they're all used up, the reaction finishes. The marble chips will not be used up in this reaction. So that's why the rate of reaction is decreasing. So at the start, there's lots of collisions taking place between the marble chips and the acid particles. There's lots and lots of acid particles, lots of collisions, a very fast rate of reaction, lots of product is being produced in a small time. As the reaction proceeds, the acid particles get used up. And as they get used up, the frequency of collision starts to decrease. As the frequency of collision starts to decrease, then what happens is the rate of reaction starts to decrease as well. And at the end of the reaction, all the acid particles are used up and the reaction stops at that point. Now we'll start to use a term later on, which is, rather than just saying the frequency of collisions increases, we'll start to use a term which is the frequency of successful collisions increases. But we'll talk more about that later on. We're just interested for the time being in the shape of these graphs that we have. Moving on to this idea of collision theory. And it's very, very important we understand what collision theory is, because this will be used to explain the effect of temperature, the effect of concentration, the effect of pressure on the rate of reaction in the next few lessons. So in order for a reaction to take place, there are two requirements. And the first requirement is that the particles must collide. They must hit each other. They must bang into each other. If they don't, then no reaction will take place. And the other requirement is that they must have the correct energy, i.e. they must have the activation energy. So two requirements for a reaction to take place are that the particles must collide and the particles must have the activation energy. You might be thinking, well, actually, what is the activation energy? And the definition for the activation energy is required for the exam. And the definition for the activation energy is it's the minimum energy with which particles must collide in order for a reaction to occur. So the activation energy is the minimum energy with which particles must collide in order for a reaction to take place. So two particles will collide, they will have the activation energy, and they will result in a reaction. Now what's very important at this point to note is that if the particles do not have the activation energy, the minimum energy needed for the reaction to take place, then no reaction will take place. The particles will bump into each other and bounce off, so no reaction will take place. And that's why often you have to heat reactions in order for them to go. And also if the particles have the right activation energy, but they need to collide with another reactant particle, and they can't react for some reason, then the reaction will not take place. The particles must be able to collide with each other, which is often why we dissolve things, and also they must have the activation energy for the reaction as well. Now I'm just going to quickly refer to this term, which is successful collisions, and the term collisions, because I think at this point it's the right point to talk about these and to make sure you can differentiate the difference between the two terms. The terms collisions and successful collisions are different. The term collisions just means that the particles collide with each other. And just because they collide with each other doesn't mean that a reaction will take place. Okay, the particles can collide with each other, but they can bounce off because they don't have the activation energy. So it doesn't mean a reaction will take place. By saying successful collisions take place, that means that when the particles collide with each other, a reaction takes place. So there's the difference. The particles collide with each other and the reaction takes place. The collision is successful. What that implies is that the particles collide and they have the activation energy. And that's very, very important. So by saying the word successful collisions take place, that means that the particles have the correct activation energy and they also collide with each other. So I'm just going to run you through the explanation with the marble chips experiment on the last slide, just to make sure we can use those terms correctly. So in this particular reaction with the marble chips and the hydrochloric acid, think about what's going on. The marble chips are in excess, there's lots of those, and the acid is not in excess. That's your limiting reagent, the reagent that will run out over time. The acid particles collide with the marble chip particles, and that's happening all the time in the flask. We're going to assume that the reaction takes place at room temperature, so the particles do have the activation energy. What we will set the start is that there's lots of acid particles, and there are lots of successful collisions occurring between the acid particles and the marble chip particles, and therefore lots of product is produced per unit time, and the reaction is very, very fast. What we then say is that as the acid particles get used up, the reaction slows down. It's indicated by a less steep line, and this is because there are less successful collisions occurring between the acid particles and the marble chip. And then what we say at the end is that all the acid particles are used up, and therefore the rate of reaction falls to zero. No more product can be produced. So the word successful is very, very important in securing your marks in the exam. So make sure you understand collision theory and make sure you use the word successful collisions when you're implying that the particles are colliding and they're reacting with each other. And that's very, very important. This concludes the lesson on collision theory. Lesson 2 will cover the effect of temperature.